be doing centripetal force. And I recall that we all enjoyed discussing centripetal force. Was that before the midterm break? Yes. And the purpose of this lab is to analyze uniform circular motion of an object of mass m attached to a string of a fixed length r. You're going to observe the relationship between the time period of uniform circular motion and the centripetal force, and you're going to determine the mass m of an object, a rotating object, by utilizing the theory of circular motion. So what is the theory of circular motion? When an object undergoes uniform circular motion, the object has a centripetal acceleration directed towards the center, which results from the centripetal force. So like we spoke of in the lecture, if an object goes around in a circle with a constant speed, then we need a force directed towards the center to take it around the circle. And we call that force a centripetal force. If you have a force on an object, then the object has an acceleration. We call the corresponding acceleration the centripetal acceleration. For an object of mass m, moving in a circle of fixed radius r, and with a constant speed v, not new, you learned from lectures that the centripetal force F is the mass times the centripetal acceleration, where the centripetal acceleration is v squared over r. So we have the equation that F is equal to mv squared over r. Very familiar? We've seen the equation before. Sorry. You also know from lectures that the speed is related to t, and I recall Denny did that one for us, that v is equal to the circumference of the circle divided by the period. So v is equal to 2 pi r over t. So we can relate the two things. We can write the top equation in terms of the t. Yes, that I think Denny had done that for us. And so when we do that all, we get that the force is equal to m 4 pi squared r over t squared. So that is relating the force to the period. Period and the force are related by F is equal to the mass that is rotating times 4 pi squared times the radius of rotation divided by the period squared. So equation 3 shows that the centripetal force acting on an object mass m, on a moving mass, m of the object is inversely proportional to its period squared. This relationship means that by plotting a graph of the force F on the y-axis, on the vertical axis, against 1 over t squared, yes, not 1 over t, not against t, over 1 over t squared on the x-axis, it will give the equation of a straight line graph. And the equation of a straight line graph is y is equal to m, and we're going to use a big M here to distinguish it from the small m, which is the mass of the object. Y is equal to mx. Well, we know plus c, but the c, there's no c in this case. So y is the f, and x is going to be 1 over t squared. So we want to compare equation 4 and equation 3. Yes, you're going to do that when you do the experiment, noting that the y is the f and the x is the 1 over t squared. So in equation 3, you can identify the y and you can identify the x, and hopefully you can identify the big M. All right, the method. In this experiment, an object of mass m, small m in this case, which is represented by a black dot, is fastened to a string which goes through a pipe, and a weight is suspended at the other end of the string, as shown in figure 1. So where is figure 1? Oh, that is figure 1. Okay, so you have a mad looking man with, okay, all right. So the black dot represents the mass. It's attached to a string that is going through this brown thing, which is called a pipe, and then the string goes down and is attached to some suspended washers. All right, okay. Okay, in order to keep the mass m of the object in circular motion at a fixed radius r, you need to spin the object of mass m at a sufficient speed v that will generate a tension force in the string, which will be exactly equal to the weight of the washer. So the washer hanging down here, yes, will have some weight, that will be a tension in the string, and that will be the force in the string, yes. Okay, thus the washer will remain stationary and the moving object will keep rotating with a constant radius. The object M moving in a nearly horizontal circular plane, the object N moving in a nearly horizontal circular plane, then we'll have a centripetal acceleration resulting from centripetal force, which in this case is simply the force of the tension in the string and thus equal to the weight of the washer. From this simulation or experiment, one can find the centripetal force, which is the force of tension, which is the weight of the washer. So we say the same thing repeatedly, so you get it. All right. The experimental method. View the classic circular force lab in the link. So you click the link. Okay, new share. Time for a new share. New share. This share. All right. So this is the simulation. This is a simulation. This lab will let you determine the speed needed to keep an object in circular motion. You will be able to change the force holding the object in a circle by clicking on the washer. Each washer has a mass of 10 grams. So if you have 14 washers, as I see down there, that's going to be 10 times 14 grams. You can adjust the radius of the circle by clicking on the masking tape that is just below the tube. You can also change the mass of the moving object using the arrow. Yes? Find the velocity of the object by timing at least 10 revolutions. When you are ready to start the experiment, you can click the begin button. So you click the begin button. Okay. So here's the experiment. It says you can click on the masking tape to change the radius. So let's click on the masking tape and we can change the radius. I think we want to change the radius to something like this. You can click on the washers to change the number of washers. Bam, 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 bam. Yes, and then you can start the experiment. And you want to time 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes? So 10 revolutions took 16.7 seconds. Very good. Okay, so that's what we want to do here, new shape. And then you're going to change the number of washers and repeat, and change the number of washers and repeat, and change the number of washers and repeat, and change the number of washers. What is this? Where are we? Right here. All right. So where are we? Right. So B, familiarize yourself with the instructions shown in the simulation lab, which we just did. Adjust the moving object to have a mass of approximately or close to 100 grams. So by clicking on the ball itself, you're going to change the mass to about 100. No. You click, there's an up and down arrow. Let me go back to that. There's an up and down arrow. When you reset, there's an up and down arrow that changes the mass of the ball. Yes? You can do a 2 share. Okay. So this up and down arrow will change the mass of the ball. So you want to change the mass of the ball to about 100 grams. And click on the tape so as to adjust the length of the string to have a radius of a radius R about or close to 150 centimeters. You will need to adjust the weight of the washer for several measurements. So start with the lowest number of washers and increase them in a way that allows around 6 or 7 measurements to be taken. Every time you click, they're just going to put on another set of washers. So start at 5. I think 5 is the lowest. And then just keep clicking each time you want to increase the number of washers. Note that for this simulation, the weight of the washers is equal to the tension, which is the centripetal force you're trying to get. You are not ready to start your experiment. Follow the steps below. Start with the lowest number of washers. We see that that is 5. Use the stop clock in the simulation to measure the time for 10 revolutions. You just saw me do that. Find the average period T of rotation. Remember that the period T is the time it takes for 1 revolution. So you divide the elapsed time, the time for 10 that you just measured, yes, in the previous step by 10. So you want to divide the time elapsed by 10 revolutions to find the period, which is the time for 1 revolution. Repeat the previous steps for each new increase in weight of the washer and tabulate your results in the table below. Now, note again, don't forget to convert everything to SI units. That is kilograms, meters, and seconds. So you measure the mass of the washers in grams, you need to convert that to kilograms, yes? And I think that's the only thing you have to convert. The centimeter, so the mass of the object itself, mass of the moving object, you will need to convert that to kilograms. The radius is in centimeters, you will need to convert that to meters. Don't forget to convert everything to SI units. Again, we tell you so that you don't forget. And then you draw the diagram of the experiment seen in the simulation, and you will need to draw a diagram of the experiment apparatus and label it, yes? You don't need to draw the map. Okay, draw a free body diagram. We all know how to draw a free body diagram, yes? The free body diagram for the mass that undergoes uniform circular motion. Then referring to equation 3, identify which variables are changing and identify what is constant in your simulation. Then plot a graph of centripetal force. So remember, you measured centripetal force, so you calculated centripetal force from the weight of the washers, and you calculated period. So you want to draw a graph of force versus period, yes, and use Excel to find the trend line. This is not going to be a straight line. To repeat, this is not going to be a straight line. Then you plot a graph of centripetal force versus 1 over t squared, and draw the trend line using Excel and show the equation and show the trend line equation, and paste the plot in the following space. Write down the slope with its units, and using the slope and comparing with equation 3, determine the experimental value of the moving mass m, and determine the percentage difference between the theoretical value being the one that's on the simulation, and the experimental value is the one that you've just calculated in step 7. And then you write a conclusion. And that's the experiment. Any questions? Any step that's not clear? Should I give you a few minutes? Any questions? No? None whatsoever? Or you want a few minutes to look it over?
I guess no questions.
Yes, no questions. Okay. So is there a lockdown this weekend?
Yeah, it is.
Yes, sir.
Okay, wow. So we have to prepare for the weekend.
All that better for the weekend.
Oh, Freeport doesn't have any lockdown, Roka.
Not at all. All we got is curfew.
Oh, wow, that's good. These lockdown things. I don't know why this people in Subis decide to spread out this virus so much. Why do people not doing what they're supposed to do and curtail the virus?
If you listen to Clint, it ain't us. It's the police and the defense force.
Is the police and the defense force spreading the virus?
And government workers, yes.
I ship a point because it's free, but when we had that big breakout like last month or the other month.
It's true, but I don't think you can. That is the police out there exposed to the public, so they are in the front lines and they're not adequately protected. I think they're trying to protect the people and exposing themselves. But Clint, I tend not to listen to Clint. You know, Clint. I think Clint needs to go back to school and educate himself.
I know in Freeport, we had that big breakout because what had happened was the police decided to throw a promotion party. Nobody had mask on, but somebody had the virus. That was
police had a party.
Yeah, the police officers, some on the other islands, some days be slack about it. They don't be just them on the front line, just be them doing full behind the scene.
Oh man.
Yeah, then they want to blame Airbnb.
I take back what I said about Clint, but I think Clint creates the wrong impression in the society, especially there was sometimes I thought that, well, the times I listened to him, he was trying to create too much sensation rather than trying to help with the solution, giving the people the wrong impression. For example, when the numbers had were corrected, all he had to say, if he was looking at the numbers, is that they just updated the number of recovered patients, and that was just the difference that you saw. He went on to say that the whole thing was wrong, and no, it's just the recovered patients were updated. That was all. Giving the people the false impression of what the government or the medical people are trying to do. I thought that was rather unfortunate. But anyway, that's a different issue. Let us get back to. I guess we're in this mess, and it is a concern. I just hope we all do the right thing. Yeah, and you're right. The government workers are a little careless. I went to license my car and I was a little concerned. Almost had to tell everybody, you cannot take out your mask to talk to me. Yes, you have to interact with me, but just keep on the mask. I will hear what you say. Don't hand me a document with my window down and come and talk to me with your mask off. That ain't right. Or your mask not covering your nose. It's almost as bad as not having a mask if the mask isn't covering your nose. They don't seem to have gotten the information right. But anyway, let me not stress you out on that. Just do what you have to do. Keep safe. What I thought we could do, at least just spend an hour or so and send you to do the experiment, or maybe just send you to do the experiment now. But maybe just look at a couple questions make some use of at least an hour. Doing some problems. Did we do questions in work kinetic energy theorem? Did we? Yes, we did this one. What is this one? A box accelerated from rest. Okay, I was just making a note of some questions that were not homework. 19 is not a homework question. 23 is not a, let's just do some problems. This is physics. Let's do number 19. Somebody read number 19 for me in the text. That's chapter 6, right? Let's do that while we're here. I wonder if I can go to Freeport for the weekend. Oh no. I can come and help you do some physics, bro. And I will wear my mask and keep social distance. Anyway, let's stay focused. I need to go to Apopia and get some water. Yeah, I'll try to do that. All right, guys, number 19, somebody please. Will you read it?
It says two identical arrows, one with twice the speed of the other, are fired into a bale of hay. Assuming the hay exerts a constant frictional force on the arrows, the faster arrow will penetrate how much faster than the slower arrow?
How much deeper? How much further?
Or how much farther than the slower arrow?
Ooh.
Yeah.
So that's a nice question. So they go into a bale of hay. I don't know how to draw a bale of hay. And you want to find the distance moved by each arrow, or the ratio of the distances moved by each arrow. Can you guess what the answer is going to be? Anybody wants to guess what the answer is going to be? I'm not going to call anybody, but it would be nice to guess. Just guess, it don't matter if you're right or wrong.
Mr.
Remember,
McDonough.
you are allowed to be wrong in the class. What's that?
You draw something on your screen because you still on the lab name.
Thanks.
Have your friends your screen free.
That's all I draw. Just two arrows, one with V, one with 2V. Oh. And what might be I don't know, just something.
So, would the answer just be twice the distance?
That's a guess. That's a guess. We will go with that guess. Any other guesses? So since one has 2 times the speed, then it says her guess is twice as far. Any other guesses? No other guesses? Going once? You're not adventurous at all. You don't gamble. So how Island Lock makes so much money? I must stop trying to be funny. Just make a guess. No, I don't try to get you to engage your mind. That's all. The way you engage your mind is by saying something. Physics is not going to be learned by not engaging mentally. It does not. And I'm sure everybody here wants to learn physics, independent of what
Yeah.
happens. You want to learn some physics. Physics is fun to learn. All right, so anybody wants to suggest which idea in physics we can use to help tell us whether the guess is right or wrong? You make a guess and then you use some physics to refine your guess. Which physics? Anybody wants to tell me which physics is important here? No, still no? All right. I'll tell you, it's the word kinetic energy theorem. I can use the word kinetic energy theorem, yes? So what does the word kinetic energy theorem say? Can anybody tell me that? No?
You mean the formula for it?
Oh, if you have a formula, I will welcome that. What is the formula for it?
Half mv. Half mv squared.
Half mv squared, yes. Half mv squared is the Ke. And what does the work kinetic energy theorem say? Anybody want to tell me? You haven't studied that yet? No? So it doesn't make sense me doing this then? Wait until you study it? Maybe? Yeah?
Work done, you say? Sorry.
What's that?
You say the formula for work done?
Yeah, what's about the formula for work done?
I don't know about that.
And what is the work kinetic energy theorem? The work kinetic energy theorem says that the work done by the net force is equal to the change in kinetic energy. It's the work kinetic energy theorem. So the work one is going to be equal to the frictional force times D1, which is going to be equal to the change in kinetic energy 1, yes, delta KE1, which is going to be equal to a half mv1 squared minus 0 or 0 minus that, because it's final minus initial. So let's say 0 minus a half mv1 squared. Remember the frictional force, oh, I should put the cos theta. It's cos theta. And since theta is equal to 180, cos of theta is equal to minus 1. So I can write this W1 is going to be equal to minus F friction times D1. Yeah. So I see that minus F friction times D1 is going to be equal to minus a half mv1 squared. And I can get rid of the minus on both sides. Similarly, minus F friction D2 is going to be equal to minus a half mv2 squared. But V2 is equal to 2v1. And so minus F friction times D2 is going to be equal, let's forget the minus sign. Get rid of the minus sign on both sides. Multiply both sides by minus 1. Is equal to a half times m times 2v1 squared, which is equal to 4 times a half m v1 squared. What do you see then? How does D2 compare to D1? Danny,
Yes, sir.
how does D2 compare to D1?
It's 4 times as much.
It's 4 times as much, yes. It's 4 times as much. So you could have guessed because the kinetic energy goes as V squared, yes? And so if you double the kinetic energy, if you double the V, the kinetic energy goes up by a factor of 4. So you didn't need all of this algebra, especially if your algebra isn't very strong. It's nice to be able to just relate things, yes? If your algebra isn't strong. So if the V goes up by 2, the kinetic energy goes up by 4. And the work kinetic energy theorem will tell you that the work is the force, and they told you that the frictional force is constant. So the distance must be, the distance must go up by a factor of 4. That's another way of thinking about it. So, is everybody okay? You're not quite there yet? You want to, what are you doing? Where are you? Where are you? You're still on circular motion? You think you'll catch up by Monday, so we can do this on Monday instead?
Yeah, I think that would be best because
Yeah, it doesn't make sense me just running through things that you're not familiar with.
yeah, because
Learning doesn't happen that way. So, all right, so review I think there's a quiz on uniform circular motion.